So welcome everybody. We've got the numbers going to start ticking up now. So we'll just give it a couple of minutes as always, welcoming people into our transition lunch and learn today, which is on the impacts of liquefied natural gas or LNG. As we have those numbers slowly ticking up, we'll just give it a couple of minutes to get the good audience settled in. My name's Rachel Hemingway. I'm the former head of the transition work here at Climate Bonds and now the head of strategic program design. So still with Climate Bonds, still working on transition, but just a little bit broader now. Very excited to be here today. Have we got the numbers coming up? Yes, we do. So I think I'll kick off. We have an hour today, and I'm really excited to be here with Professor Howarth. So Professor Howarth has been instrumental in our work at Climate Bonds over the last few years because he's been a tireless fighter to expose the true impacts, the true environmental impacts of methane and particularly liquefied natural gas. So he's going to talk in a lot more detail about that over the next half an hour or so, and we're going to have some time for Q&A at the end. So please do throw your questions into that Q&A box. My colleagues will be monitoring LinkedIn Live as well, so please do feel free to ask any and all questions that you want to, and we'll try and get to them at the end. But just to give a little bit of context for this chat today, for a very long time, the only greenhouse gas that was really considered was carbon dioxide. So it's the only greenhouse gas that was talked about. We always talked about carbon emissions, and we only really thought about greenhouse gas emissions from the burning of whatever fuel it was, be that coal or oil or gas or wood. But this means that there's been a very narrow focus on carbon dioxide emissions coming from the combustion of the energy source. But other equally important emissions have been ignored, they've been glossed over. And this has led to a situation where emissions from fossil gas, which is methane, have been downplayed because fossil gas, when it's burnt, is relatively low CO2. But fossil gas leaks methane along the entire supply chain. And methane, the climate impact of methane is much, much higher, as Professor Howarth is going to talk about, than carbon dioxide. Now, oil and gas companies and others have been promoting gas as a clean or a transition fuel able to replace coal in our energy needs because it is low emissions. But because methane is such an important climate forcer and the emissions of methane come from along the whole supply chain, that claim that fossil gas and methane is a low impact fuel are wrong. Now, LNG, liquefied natural gas, it's exploded in popularity in recent years, partly in response to a need to replace coal, and partly because LNG is quite easy to transport because it can be liquefied. So we're going to explore this a bit today. Professor Howarth from Cornell University is going to talk about the climate impacts of LNG, and then we're going to talk about what does that mean. So if LNG is a really high forcing greenhouse gas, what does that mean for all of the investments that have been piled into LNG infrastructure in recent years? So, Professor Howarth, I'm very happy to hand over to you. I believe you've got some slides to talk us through today. And again, for the audience online, please do share your questions in the chat and we will get to them at the end.
Thank you, Rachel. A great introduction to the issue. And I'm going to be talking about fossil gas and how it's transported in liquid form. As Rachel has said, fossil gas is mostly methane, and it's really impossible to develop and use gas without having some of it emitted unburned to the atmosphere. Methane is more than 100 times more powerful than carbon dioxide on a mass for mass basis for the time it's in the atmosphere. So that's a really, really big problem, and it was underappreciated for quite a while. I've been working on various aspects of that for about 15 years, and we'll get a little bit into the details here. So next slide, please. I just want to start a little bit with the climate change aspect, and this is from the Intergovernmental Panel on Climate Change, the United Nations organization that brings together the world's leading climate scientists. The most recent synthesis we have is from 2021, 2022, and they show unequivocally that the Earth is now warmer than it's been in any time in human society. It's warmer than it's been in the last 100,000 years. And it isn't just warming. Of course, it's important. The climate is becoming increasingly erratic. It's being disrupted. The warming is overwhelmingly due to fossil fuels, as they say, both carbon dioxide and methane being released from it. Most of the warming, most of the climate disruption has occurred since 1980, which is ironic for me because 1980 is when I started teaching about climate change, and it's only gotten worse in the time since I've been working on it. But what this slide shows is that without the greenhouse gases from burning fossil fuels, the Earth would be very, very steady in temperature over the last 100 years or so. And the warming that we're seeing is clearly due to fossil fuel combustion, and we understand that very, very well. Next slide. Now, the final sentence from the executive summary of this IPCC report from 2022 is just crystal clear, and I want to read it. Scientific evidence is unequivocal. Climate change is a threat to human well-being and the health of the planet. Any further delay in concerted global action will miss a brief and rapidly closing window to secure a livable future. That's as of 2.5 years ago that was written. So we really have to move on this climate disruption. Next slide. And of course, the nations of the world came together a little under 10 years ago now in Paris for the COP United Nations meeting, agreed that any warming above 1.5 degrees Celsius was dangerous to the future of society, and agreed that we should keep the planet well below 2 degrees Celsius. Next slide. And I just want to explain a little bit. I was at the COP21 in Paris and participated in those discussions, and I want people to understand where that 1.5 degree and 2 degree comes from. These are what we call tipping points, fundamental thresholds in various aspects of the global climate system. Things like losing Arctic ice in the summertime is on the left. I won't go through these in detail, but what I want you to see is that this was the thinking going into COP21 from 10 years ago. The thought was that if we keep the temperature in the white range here, that we're moderately safe on these tipping points. As we hit temperatures in the yellow for each of these, we run the risk of runaway climate disruption, and in red, we certainly will have runaway climate disruption. So again, you see there that 1 to 1.5, 2 degrees becomes worrisome in terms of things like Arctic ice, Greenland ice, et cetera. Next slide. And we've been continuing to warm. This shows the warming right up until about a month ago. It looks like perhaps we've hit the 1.5 degree target right now. Certainly last year was more than 1.5 degree above the baseline. Scientific community is debating whether or not that'll dip down a little bit. Maybe it'll be a few years before we stay above 1.5, but we're right at that dangerous point now. Next slide. And I want to stress that we were optimistic in terms of the risks going into COP21. I really want to pay attention to this one on the right, which has a fancy name, Atlantic Meridional Overturn Circulation. What that means is that the fundamental ocean circulation, particularly in the Atlantic, but globally, is thought to be at risk of changing as we hit about 3.5 to 4 degrees Celsius. That's what we thought a while ago. Turns out that we're actually now seeing that change at 1.5, and there's good evidence that the North Atlantic circulation has slowed by 15 to 20% over the last decade. That is very, very worrisome. So bottom line is we really have to keep the planet cooler than it is. Next slide. And this is from paper, Washington Post reporting on papers in Nature that were published about 7 years ago, as it first started to become clear that we are already hitting that threshold at 1.1 degrees, not 3.5. Next slide. Okay, so let's turn to LNG, liquefied natural gas. LNG exports from the United States were banned until 2016. We became an small exporter in 2016, but the exports have accelerated hugely since then. The U.S. has become the largest LNG exporter globally as of 2022, and our exports continue to grow rapidly, and industry wants them to grow even faster than they are. Next slide. And this just shows trends for various countries and changes from 2018 up to 2022, 2023. And what you see is that as of 2022 or 3, the biggest exporters are the United States, Australia, and Qatar. And in terms of change, it's all in the US. Other countries are relatively stable in what they're doing. And the US exports have actually doubled since that 2022 number. So we're a driver totally in what's going on globally with LNG exports. Next slide. Now, I published a paper on what the greenhouse gas footprint of that LNG export is. My paper was finally published this last October, but as I note here on the left, I actually submitted the paper 11 months earlier than that, and I was convinced by colleagues and activists to make my paper publicly available even before it went through peer review and was published. So I did that in November of 2023, and we'll come back to why I did that later. One result that made my job a lot harder. This went out for peer review. It went to about the most extensive peer review I've ever seen. I've published 200 papers in my career, and this one got more scrutiny and oversight than any other because it's a politically hot topic and because it was publicly available as it was being reviewed. Next slide. So a little bit more background on U.S. gas production, gas use, where it's coming from, and whether we're a net importer or exporter over time. So we're looking here from 1950 up to 2022, and the top two lines there are the consumption of gas in the United States and the total production of gas in the United States, and you can see that our consumption exceeded production for the period, say 1990 through 2010 or so. Natural gas production started rising rapidly in the 2005 to 2010 period. That's because of fracking, high volume hydraulic fracturing in the United States. It was not possible to develop shale gas before that. And you can see that the line labeled production of shale gas, very, very rapid increase in shale gas production starting 2006 or 7 or so. The total production of gas includes that production of shale gas. So what you see is that overwhelmingly now, most of the gas that's produced in the United States is shale gas. It's a very energy intensive process for getting that. High volume hydraulic fracturing takes a lot of energy to break up rock. The wells for these are much, much deeper, longer than traditional wells. So a huge amount of energy going into that. As of about 2016, the production of gas started to exceed consumption of gas in the United States, and that's when industry pushed hard to lift the ban on exports of LNG. So we were a net importer of gas until 2016, and we've become a net exporter since then. Next slide. So liquefied natural gas in the United States is made almost 100% from fracked shale gas. Most of the global increase in natural gas production, fossil gas production, over the last decade and a half has been the United States, and it's been shale gas. And that increase in shale gas production has greatly increased the amount of methane that's going into the atmosphere. at least a third, perhaps half of the total increase in atmospheric methane over this last 10 to 15 years has been from shale gas development in the United States, and it has had a measurable climate impact. According to the IPCC again, a third of all global warming since the 1880s has been from methane, as opposed to 50% from carbon dioxide. So yeah, carbon dioxide is a little bit more important than methane in global warming, but not by much. And when we're looking at changes globally in greenhouse gas emissions, what we're doing with fracked gas in the United States is key. So,
Howarth, can I ask a question on that one?
absolutely.
So you were saying that producing fracked gas is really, really energy intensive.
Yes, it is. Yeah, because the shale gas is methane that was left in the deep shale formations way underground, say maybe 8 to 10, 12 kilometers or more deep. And until 2005 or so, it was not possible commercially to develop that. And there are two technologies which allowed it to happen. One is high precision directional drilling. It's incredible evil, if you like, but incredible technology. It's probably on timer there. Sorry about that. The industry can go down, drill many, many kilometers into the ground until they find these shale formations, which might only be 10 meters thick. They go on for hundreds of kilometers, but they're only 10 meters thick. They drill into them, then they turn the well laterally and drill sideways through it for many, many kilometers as well. So a tremendous amount of drilling. That takes a lot of energy. And then they break up the rock by putting down massive amounts of water and chemical additives to fracture it, high volume hydraulic fracturing. And that also takes a tremendous amount of energy. So it's not like your conventional gas. It's the carbon dioxide emissions associated with all that energy that's needed to do the fracking and drilling are significant. Plus methane. You got methane emitted all along the course there of doing so.
So it's inefficient as well then.
It's inefficient, and
Hugely
it's
inefficient. You're only getting
most of the most of the global increase in gas production over the last 15 years has been from this source, fracking in the US, which I don't think people realize. We're now the largest gas producer in the world. We're also the largest oil producer in the world, and we were not 10 or 15 years ago. We produce twice as much oil as Saudi Arabia, which I don't think people realize. But back to gas
massive,
for today, right?
massive impetus to keep it going. Okay, yeah,
Absolutely.
interesting. Carry on. Sorry.
Oh, I think I just talked to this slide, so it's energy intensive. Next slide. So now to LNG. LNG is taking the fossil gas and supercooling it to put in liquid form so you can carry it in tankers. It's too difficult to transport as a gas. Takes a lot of energy to liquefy it. Paradoxically, when you warm it at the destination port as well, that also takes energy to turn it back into a gas. And of course, it takes energy to move it by tanker. And most of those energies, all of the energy for liquefaction, the regasification, and as well as most of the energy for the transfer by tankers, comes from either burning LNG or burning fossil gas that would otherwise be consumed. So we're not talking just about the final gas that's burned by the consumer, say in Europe or Korea or wherever. There's a huge amount of gas that's burned to power this whole thing. And because of that, it takes more, the more emissions associated with that production of the gas upstream from the fracking process, and there's more methane emissions associated with that relative to the gas that's delivered. So these upstream emissions of both carbon dioxide and methane become important when we look at the greenhouse gas footprint of LNG.
And
Next slide.
all this infrastructure, this liquefaction and regasification infrastructure, and the ships that are designed to carry LNG, are these specific for LNG, or is there any other purpose that they can be put to? Because there's
No, that's an excellent question, and
billions
it's
going into this.
highly specific. There's no, it's a very, very expensive infrastructure. These ships are very expensive. They cannot be used for anything other than carrying LNG, and both the liquefaction facilities and the regasification facilities cannot be used for anything other than LNG. So, a ship may well be a billion-dollar investment. Loading
Mm.
port might be a 4 to 6 to 8 billion-dollar investment, and its only use would be for LNG.
So this is high risk for
I,
from an
I think
investment.
it's
Yeah, this is
extremely high
high
risk.
risk.
Yeah, I'm not an economist. I'm a climate scientist, but
Yeah.
yeah, absolutely. We can
But
come back to, yeah.
yeah, sinking billions into infrastructure that is potentially or very likely to be stranded because of the climate impacts of what it's carrying is
If we care
well,
about the climate, and we have to, then yes, this will become a stranded asset. The only way it would not be a stranded asset is if we just throw up our hands and go, let the climate do whatever, which would be
well,
devastating to society.
and the economy, which is what a lot of people care about. But yeah, sorry, carry on.
Okay.
I'm asking questions because I'm really interested about this,
No,
but
that's good. I appreciate it. Next slide. And also there's methane emissions from tankers themselves in addition to that. And this is kind of a detail, but I'll come back to it. About half of the tankers in the world uh, are steam turbine engines, fairly old technology, 20-year-old technology to be precise. The industry is very proud of having more modern two-stroke and four-stroke engine technologies, which are more fuel efficient and so have lower carbon dioxide emissions, but they aren't so good at burning. They burn LNG for their fuel. They're not very efficient at that. And so unburned methane is coming out in their exhaust, which engineers call slippage, and that's significant. Next slide. So I just want to highlight that we have a really good handle now on these methane emissions from the fracking and developing of shale gas, these upstream and midstream emissions, we call them. And I published a paper on this as a problem 14 years ago. That was the first paper ever published on the topic. Industry hated it. They said, no, it's wrong and all. There've been thousands of studies since then. And for my paper, I relied on a fairly simple review that I'd published back in 2022 based on about 1,000 observations on the left there. During the time my paper was out for review, a much better synthesis was published in the journal Nature last March. And so I switched and revised my paper using it. Didn't really change the numbers much, but the new synthesis is based on close to 1 million observations on methane in the U.S. associated with shale gas. So we really know what these methane emissions are with some precision, and that's what I used. Next slide. So data. What you're looking at here are 4 different types of tankers, and for each tanker on the left is a short cruise, say from coast of Louisiana to Ireland, and on the right would be the longest cruises to China. And we're looking at the dark blue is the carbon dioxide that's released as the fuel is finally combusted. That yellow color is carbon dioxide other than from the final combustion. So what the tanker is releasing, what's used for the fracking processes, compressors to move the gas, the liquefaction process. And the red are the methane emissions, a lot of them upstream, but also from tankers converted to carbon dioxide equivalents. And what I really want you to see here is that the final combustion, it's non-trivial for sure, but it's always less than half of the total emissions. So these upstream and other emissions of carbon dioxide, the indirect carbon dioxide emissions, and the methane emissions are really critical. Next slide. And in fact, next slide. Whoops, can you go back one? Oh, back one more, I'm sorry. Yeah, there. These upstream and midstream methane emissions and carbon dioxide emissions combined make up about half of the total emissions here, more than from the final combustion. So it's the fracking process and all of the energy that's needed for the liquefaction and for the tanker transport that makes this such a bad fuel. Next slide. I just want to highlight again that it really doesn't make too much difference what type of tanker you use. Industry says that they're getting better and better with these more modern tankers. The oldest tankers are the steam turbine ones there on the left. The most modern 2 types are in the middle. And you can see it really doesn't make a huge amount of difference. If you have a really good eye, you'll see that the carbon dioxide emissions go down very, very slightly. The indirect carbon dioxide ones from the tankers go down a little bit in the more modern tankers, but the methane emissions go up because of the poor combustion. Doesn't matter. Industry will tell you that they're on trajectory to make this near zero emissions. It's just not true. Next slide. So if we compare these greenhouse gas footprints from LNG with other fuels, this is all relative to the final energy that's released. I'm looking at average tanker cruises here. So shortest cruises and longest cruise distances for the average for the different types of tankers. And we're comparing it with natural gas, coal, and diesel oil. And you can see a similar footprint for natural gas, coal, and diesel. They're all about the same. But LNG is substantially worse than any of those. And in fact, the greenhouse gas footprint is about a third worse for LNG than for coal. And it's worse than for natural gas used domestically. It has to be because you have all of the consequences of natural gas combined with using the natural gas to power the liquefaction and the tanker transport. And I want to highlight that we really do have a much better alternative there. Heat pumps used for heating, and that little bar on the right is the carbon dioxide emissions. We're using heat pumps in Europe on average. If the heat pumps were driven by electricity using the average grid mix in Europe, so which includes a lot of fossil fuel combustion. If the heat pump were powered 100% by renewable electricity, you would have a zero footprint. But even with the grid mix as it exists in Europe today, heat pumps are far better alternative than anything else. And LNG is the dirtiest fossil fuel out there, plain and simple. There's no other fossil fuel that matches it for a dirty greenhouse gas footprint. Next slide. I should add that, well, as I said this, LNG's footprint's 33% worse than coal. There is a time aspect in this, and I'm comparing methane emissions for a 20-year period after they're emitted to the atmosphere. The industry and many governments will tell you that we should be using a 100-year time period. I think that's wrong, and it severely underestimates methane emissions. IPCC is telling us that the 20-year time period, which is what I'm using, is better. But even if one were to use a 100-year time period, the LNG footprint is still as bad as or worse than coal. Next slide.
Just on that time period, because this is something that pops up quite often. Now, action has to be taken really quickly to combat climate change. Like,
Right.
it has to happen now. It can't happen in 20 years. It can't happen in 40 years. It can't happen in 60 years. So is this part of the reason why you think that we need to be using that 20-year warming impact rather than that 100-year warming impact?
Well, that's certainly important. We don't have, we are maybe at that 1.5 degree COP21 target already. If we're not at it, we're going to be at it in a couple of years. If we keep using fossil fuels at the current rate, we're going to be at 2 degrees Celsius from the pre-industrial baseline within the next 20 to 25 years. We're not talking a century off. So that's part of it. But more importantly, again, the IPCC tells us that a third of all of the global warming that's happened since the Industrial Revolution started in the 1800s has come from methane. If you use the 100-year time frame to calculate the role of methane, you greatly underestimate that. You say, no, methane's only caused about 6 or 7%. And the 20-year time period, it doesn't do a perfect job either, I want to be honest, but it much better captures the history of what methane has really done.
So you're looking at like the observed impact rather than,
Yeah, exactly. I mean, the issue is that methane is an incredibly potent greenhouse gas that absorbs infrared radiation at more than 100 times that of carbon dioxide, but it doesn't stay in the atmosphere for as long. It's got a half-life of about 12 years. So in 12 years, half of it's gone. If you put a pulse emission in 24 years, 3/4 of it's gone, et cetera. So it doesn't entirely disappear, but if you take that pulse and average its climate impact 100 years into the future, you are, severely downgrading the period 70, 80, 90 years out after the methane's disappeared. That methane's going to have a huge whammy in the next 25, 50 years.
And so, I mean, linked to that, by stopping that methane emissions, you're also having a huge positive climate impact in the short
Mm-hmm.
term. So
Yes.
it's kind of it's win-win. You can stop it to prevent the future climate impacts, but it will also start to have a potentially more short-term positive impact on the climate. So
No, exactly. And we're getting into the weeds a little bit here on what's going on with the climate, but
yeah, sorry.
the climate is not fine. The climate's warming faster than most climate scientists would have been predicting 5 to 10
Mm.
years ago. And a good case can be made that's because of methane. You know, methane emissions globally were actually flat for the first decade of this century. They've been going up for the last 15 years or so. As I say, fracking in the US is a major, major driver of that. And that short-term whammy from methane is a major contributor to the warming we've seen over the last 5 to 10 years.
Thank you.
How am I doing on time? I can cut this shorter or keep going, or how would you
No,
like?
you're good. We're at half an hour left,
Okay.
so we're
Well,
fine. We've got a couple of
let
questions
me.
coming in, but carry on.
I just want to show this. This came out after my paper was published, and it's a really creative use. The people who pulled this together took global satellite uh, visions of methane emissions. And satellites, methane's an invisible gas to the human eye, but satellites can pick it up by looking at the infrared spectrum. And they superimposed that with satellite tracking of ships and sort of laid one on top of the other. So what you're seeing there is a tanker, LNG tanker that's being loaded, and that thing that looks like smoke going off to the upper corner there to the right is actually methane. It's a plume of methane, and you know well, I'm showing this because I assumed that the methane emissions during the loading process were fairly low. The data were not available at the time I wrote the paper on this, and I was being conservative. So absent strong data, I assumed that things were on the up and good side. As information becomes available, it's looking like I was too conservative, and the greenhouse gas footprint is probably worse than I said. That's the message from this slide. Next slide. Okay, so again, I published my paper finally came out only October this last year, but it had been available for 11 months before that publicly. Next slide. And Bill McKibben in particular, the activist and author, publicized my paper heavily in a series of articles, trying to get the attention of the Biden administration because under US law, as of the end of 2023, January 1st, 2024, the US could export more LNG only if the Biden administration certified that it was in the national interest to do so. And Bill McKibben was pointing out that based on my climate research, it clearly wasn't in the national interest. Next slide. And the Biden administration paid attention to that. And in January of 2024, they put a pause on any further LNG exports. Plenty of LNG coming out, but they put a pause on increasing the capacity, stepping away from the Obama policy, the LNG exports that started under President Obama, actually. And Biden said, you know, this has to be further studied by the Department of Energy, looking both at climate and economic concerns. And the Department of Energy, well, the next slide. My paper was clearly a factor in that. Biden himself held a press conference announcing that pause. He didn't mention me by name, but he did say new research coming out of Cornell University, and I'm the only person at Cornell who works on this, so it was my work. Next slide. And again, they were using an early draft of my paper, but my final conclusions were very, very much the same. So the Department of Energy finally came out with their analysis as ordered by Biden. It came out 2 months ago yesterday, and they very, very much come out saying that LNG is not good for the world, not good for the climate, not good for the United States. Next slide. And I just want to highlight some of the details of that. the then Secretary of Energy, Granholm, issued a very, very strong letter associated with the report. And I want to highlight a couple of points here. Again, this is just from 2 months ago. She very clearly says that the report coming out says that it's a bad idea to continue to follow the business as usual approach for LNG. It's neither sustainable nor advisable. And she has 5 key findings behind that. Next slide. First, she says that the growth in LNG exports in the United States has just been staggeringly remarkable. And we should be cautious going ahead because this has all happened so quickly. And the last sentence here, she says that the quantities already approved without further government approval for export are equal to roughly half of the U.S.'s total current natural gas production. Now, we're not yet exporting half. We're exporting about 9% of our current production. But what the Biden administration is doing was pausing increased capacity growth, worried about those stranded assets we talked a little bit about earlier. If we were to live up to the capacity we already had, it would be half of U.S. consumption. That's staggering. Next slide. She talks about the economic aspects. If we were to increase LNG exports even at the rate that we have current capacity for, the studies estimating it would increase the cost of natural gas domestically in the U.S. by 30%, increase the volatility to U.S. consumers. So far, we probably have about a 5 to 6% increase in energy prices in the United States because of our LNG exports, but it could get far, far worse, be far, far more noticeable to U.S. consumers. And she's saying, as U.S. consumers wake up to this, we probably will not be able politically to continue to export LNG. Next slide. Third, both the fracking operations and the LNG facilities are typically in places where communities are burdened by pollution, environmental justice issues here, and that without a big increase in the regulatory framework on this, that this will have a huge public health aspect on communities. Next slide. Fourth, there's the climate aspect, which was what my paper was about. Bottom line is that the Department of Energy study more or less endorses my findings, although they say perhaps we should be using that 100-year time period instead of 20 years, so they quibble some. I think they're wrong on that. I think they're underestimating the potential. But critically, they point out that the real issue is not whether LNG is exported in the U.S. to displace coal. LNG exports from the United States primarily are displacing renewables. And so the future choice isn't coal versus LNG, it's coal and LNG versus renewables. And they very, very clearly say that we need to stop both coal and LNG if we're at all serious about climate change. Next slide. And then finally, they address where the gas is going. And a lot of the argument has been that we should increase LNG exports to Europe because of cutoffs of Russian gas following the Ukraine invasion. But the DOE points out that European demand for gas is actually going down very, very rapidly. There isn't a need for further LNG there. There actually are other major markets are Japan, Korea, demand is also going down there. China is a major market, but they're becoming self-sufficient in gas and perhaps don't want to be dependent on LNG. So if you look globally at where the LNG demand is predicted to go up by industry, it actually is not places that are buying LNG from us now. It's places like Southeast Asia, Thailand, Vietnam, Malaysia, and South Asia, India, places which historically have not used much gas. And that's where industry is really looking to increase their market. Next slide. She released this study, of course, after Biden was stepping down from the presidency after Trump won the election. And so she's highlighting that, yes, Trump is likely to allow further LNG exports, and that's true. They've already reversed the Biden administration ban. And Trump is putting heavy pressure on countries like India to take LNG from the US in order to reduce tariff threats that he's making. But Secretary Granholm points out that if LNG continues to grow at the rate that industry wants, it will have impact of the climate. It will have noticeable impacts on U.S. consumers and U.S. energy prices and prices of everything domestically in the U.S., and that our country is likely to respond to that. So her final sentence there, the question is not whether the U.S. exports policy will be forced to respond to these interests, but when and what that response will be. And I would echo her. We might try to increase LNG exports for the next few years under Trump, but it is not sustainable. And meanwhile, the world is building an incredibly expensive, specialized infrastructure, which I can't imagine will be anything other than stranded assets as in 3 to 5 to 8 years, the people of the United States wake up and go, we really don't want to be exporting this LNG when it's bad for the climate and bad for us economically at home. Next slide. That's pretty much the end. I just want to point out that I'm not popular in oil and gas circles for this. The Wall Street Journal did a little special saying just how much the gas industry dislikes my pointing out that methane is important, but my scientific colleagues are with me on this. The science is quite strong. Next slide. So that's it. LNG is really, really bad for the climate. It's got a larger greenhouse gas footprint than any other fossil fuel. And if we want to address climate change, which the climate scientists of the world tell us we must and must do so quickly, we need to move away from all fossil fuels as quickly as possible. And LNG should be the first thing we move away from. So very happy to have been able to talk to you this afternoon.
Fantastic. That was brilliant. Thank you so much for sharing your research on this. I've had some questions come in. There's a couple of points that I want to highlight before we go to the questions. The first one of the things that you said is less than half of the emissions impact from LNG comes from the end burning of the LNG. So less than half.
Yeah, well under half. It's actually less. It's about 35%, in fact.
And one of the things that makes me think about is how much energy is being wasted from production to use along this whole supply chain. How inefficient is the use of energy as LNG as an energy supply source when you're even
It's partly that's a great point, and part of it is the inefficiency, as you say, because it takes energy to drill those deep wells and long wells. It takes a lot of energy to frack. It takes energy to move the gas in the pipelines, to liquefy it, to move it in tanker. But the methane is a big part of it, which isn't so much about inefficiency. It's the ability to hold on to that methane. And I didn't get into any details on the numbers there, but the methane emissions are driven by what goes on at the fracking sites and in the pipeline systems. And the number I'm using is that 2.8% of the fossil gas production is emitted unburned to the atmosphere as methane. So 2.8%, that looks kind of small, but because it's such a powerful greenhouse gas, it has that large impact. And I'll anticipate a question, since I get this all the time. Don't you think we could reduce those methane emissions? Industry tells us we can do better and better. In fact, they tell us they are doing better and better, which is not true because we have good data. We can measure methane emissions by satellite now. The fact is that most of those methane emissions, that 2.8%, are not leaks. If there's leaks, it suggests you just go out there with a bigger wrench and tighten up the joint or something. Most of it's a purposeful part of operations. So let me give you one example. When you do maintenance on a high pressure pipeline, You can't go out and weld when it's full of methane gas because it'll explode.
Yeah.
So you have to take all of the gas that's in the pipeline and put it somewhere. And the only technology that exists is to blow it off to the atmosphere.
That's it. That's the only way you can
That's
remove
the
it.
only one that the industry has not developed another approach for this. So it doesn't happen every day. It's only when you go to do pipeline maintenance, but it's a significant part of that 2.8%. And it's not a leak. It's a purposeful emission. And other things, when you look at processing plants and storage facilities, in order to keep them safe, keep the pressure under control, they have to release gas periodically.
Mm.
And they either release it as unburned methane, or they do what's called flaring, which is to light that methane on fire and burn it to carbon dioxide, which is better in terms of the methane, except that the flares go out. They go out routinely, and the flares aren't 100% effective at burning the methane either. And so industry really has not come to grips with how to keep those flares going, how to make it burn better. It's this technology that's 100 years old. They haven't really put any serious effort into doing it better than that. And to me, it's too late to be trying. We need to just move away from fossil gas. We can move to 100% renewable energy future in the time period of the next 20 years. And
Yeah.
that's where our financial resources should be going.
But there's a lot of sunk investments in
A lot of
LNG and it's increasing. And this is why we have to tackle this head on now because investors are blinded maybe by the arguments from the companies saying it's a clean gas, it's a sustainable gas, it's got a future. So they're willing to sink their money into these horrifically expensive pieces of infrastructure. As you mentioned, the ships, the pipelines, the liquid, I can't say that word, I don't know why.
Yeah, I stumbled over it during my talk too, if you noticed.
Yeah, and you
Liquefaction.
haven't got any excuse because you've been saying that word for a lot longer than I have. Anyway, the things that need to liquefy the gas and then regasify the gas, these incredibly expensive pieces of equipment. And as you said, the market in Europe is already moving away. So the demand for gas in Europe has been falling. It's being
Hmm.
replaced by renewables and just by policies that restrict the use of gas. So there's already an oversupply in Europe. And as you said, industry is desperately looking for new markets and they're looking to Asia. Now, there's a lot of problems with the Asian market, and one of them is these liquefaction and regasification plants are very expensive, and the onshore ones are more complicated than the offshore ones. So they're pushing for these floating pieces of infrastructure. But these are in some of the most vulnerable countries,
Hmm.
most vulnerable regions to storms and intense and extreme weather events, that the long-term costs and the long-term shutdowns of these are going to really impact the return on investment. But
Yeah.
I've got a few questions, and one of them was actually related to your flaring point. So this is from Valerie Kiccini. Apologies if I pronounced that wrong. What would be the impact of no flaring regulation in the US to the overall fossil gas carbon footprint as it is in other countries such as Canada?
Well, I mean, Canada does flare gas, and I'm not aware of anywhere in the world where gas is being stored and processed without either venting or flaring. Venting is emitting it unburned to the atmosphere. Flaring is when you burn it as you release it. And the flaring, in terms of the climate consequences, the flaring is a better alternative because it is consuming some of the methane, but not 100% because it doesn't burn effectively. Industry, flaring is extremely noticeable. You can have flames shooting hundreds of meters into the air, and it can sound like a jet engine taking off. When they vent it, it's an invisible gas. You can't see it, and you don't tend to hear it the same way. So I am told by industry insiders that although many places they're supposed to be flaring it, they often prefer not to because they get fewer complaints. And of course, there are other issues with flaring. You're producing local air pollution, nitrogen oxides, things like that. So it's both bad. But there's nowhere in the world where they don't have to release some gas for safety reasons, pressure controls. You could have better designed facilities, so it's less of an issue than in poorly designed facilities, but you're always going to have some releases.
I got a few questions on our Zoom Q&A. The first one is, what is the energy return on investment? So the energy that is needed to be invested to return 1 unit of energy for LNG as compared to oil or other just like fossil gas that's piped.
Yeah, that's a great question. I actually calculated that when I wrote the first draft of the paper, but that was a year and a half ago. And off the top of my head, I'm not going to give you a number because I won't be quite right. But the energy return on investment for LNG is clearly worse than for conventional fossil gas. Again, because you have to liquefy it, regasify it, and all. And it's substantially worse than for oil or coal as well. So exactly what the numbers might be 1.3, 1.4, that kind of range, but I don't want to be quoted on a specific number.
Fair enough. And question from the same person, Anna Diaz. What part of the total life cycle assessment is covered by the number you are showing related to the footprint? So I think this is coming back to when you were comparing the different fuels, LNG versus coal versus gas versus oil versus potential heat pump. So was it a full, is this a full LCA for each?
Well, yes, it is. And I didn't go into much detail there, but I'm looking at the total emissions to produce electricity in each case. And I should point out that, in fact, most gas globally and most gas in Europe isn't actually used for electricity, but the coal versus gas comparison generally is done in terms of electricity. More gas in Europe or in New York, where I live, is used for heating. And the emissions there are greater because, although I've sort of downplayed the idea of leaks, when you talk about pipelines going into cities and suburban areas, the pipelines which carry that are very, very leaky. It basically would double the methane emissions in an average US city. I didn't get into that in the paper because we have very poor data for what those emissions are outside of the United States. And I again want to be conservative. A new industry would try to criticize anything they could, and I didn't want to make it easy for them. So I stuck to the electricity part, which keeps you away from those final pipeline distribution leaks.
Well, I mean, based on the number of stickers which are smell gas, call this number, I think you can be fairly
Well, yes,
confident that
exactly, right? Yeah. No, and
the
in
leaks
the
under
US,
license
it
settings.
varies. We have good data. Somewhere between 1.5% and 4% of the gas entering a city is emitted as leaks from those pipeline systems. In Europe, there's one study in Paris that suggests it's comparable, and I've seen unpublished stuff for London and Amsterdam suggesting it's comparable, but it hasn't been published, and I didn't want to weaken the paper by using unpublished data.
And talking about pushback from industry, particularly, there's a question here from Cynthia Wang, which is particularly extensive peer review. What were the sticking points in the process? Were there parts of your research that were particularly picked up on, and which parts were those? And was the
Yeah.
methodology questioned and why? And what is the reception to your research been by government and industry? But what in particular were the disagreements around, and what evidence did they use to support their disagreements? So it's a good question. It's a challenging one to answer in 5 minutes, but
Yes, yes, it is. Well, let me start with the first part of it, and you can remind me about the rest. Uh, normally, when one submits a paper to a peer-reviewed journal, you get reviews back, usually 2, maybe 3 reviews. These are from anonymous people. The editor keeps their identity secret from the author, and then the author responds, and if the reviews are too critical, the editor will just reject the paper. Otherwise, they'll suggest how you try to deal with that. In my case, I went to 5 rounds of peer review. Usually it's 1 round and your paper's accepted or it's rejected at the outset. I went through 5, and that's really not because the reviewers were more critical than usual. It's because, uh, you know, I was quite transparent by the fact that my paper was publicly out there and in sight. And by the time most of this review had gone on, Biden had already cited my paper as a reason to put a pause on, right? So the editors wanted to be super, super careful. And they kept picking up. Normally, for a peer review, you're going back and forth with the same peer reviewers until everyone's happy and you address their concerns. In this case, none of the reviewers ever raised anything that was all that severe, and I was able to deal with it. But then they'd say, but I'm not really expert in this other area. And the editors would pick up on that and go, oh, we better get people in that other area as well. So I kept getting a new set of peer reviewers. I ended up with about 8 different individuals with widely different expertise. Some of them are clearly expert in the tanker technologies. And in 1 or 2 drafts of my paper, I misunderstood some of the modern technologies about how 2-cycle versus 4-cycle engines change in their exhaust stream for methane, for instance. Those aren't huge criticisms, but I was wrong, and the reviewers pointed that out, and the papers improved from it. I also, as I say, switched from my own review of the methane emissions from the upstream shale gas and used this paper that came out in Nature that caused the editors to send it back to new reviewers in that area to see if I was doing a good job on that or not. And one of the reviewers there pointed out that I could have made my argument stronger in a certain way, and I did. So it was a slow, it was difficult. I made life difficult for myself by making it publicly available. But as Bill McKibben told me at the time that he helped convince me that I should, Biden's going to make his decision in December 2023, January 2024. If you follow the normal secretive process of peer review and publish your paper in the summer of 2024, no one's going to look at it. It's not going to have any value. And so you really need to be more publicly out there. And the industry suggested it's unethical for me to have done so. It's nothing unethical about it. In fact, most professional science societies now encourage authors to do it. Generally, most of us, most of the time, don't, because it makes the job of responding to peer reviewers more difficult. But it's not an ethics issue. It's a laziness issue, really.
It sounds like the review process simply strengthened it and strengthened
Yeah,
your
it
arguments
didn't
and highlighted.
fundamentally change anything. If you look at the first draft versus the final draft, the numbers are comparable. Some of the details switched around a little bit here. The description of what tankers is doing was inaccurate in the beginning. I misunderstood some of the technologies there. That's much, much stronger. It doesn't change the numbers, but it changes how I talk about them. The crux of the matter is the upstream, what's going on in the shale gas fields and all, and that fundamentally didn't change. I used the updated information, but that area of science is pretty settled after 15 years, and it's something I've been heavily engaged in. I've published maybe 7 or 8 papers of my own in that topic before, so this is not new to me.
I think just one final question. I'm convinced I can guess your response for this, which is, how do you see the industry promotion of what is known as blue hydrogen as a low carbon alternative?
Well, I published a paper on blue hydrogen back in 2021. So if people want to look at my paper, you can just go Howarth Lab, all one word, .org. And my papers on blue hydrogen are there as well. Blue hydrogen has a very, very large greenhouse gas footprint. It's not as bad as LNG, but it's worse than natural gas. And the marketing by oil and gas interests saying it's low or zero footprint are just completely bogus, completely bogus. Marketing, it's not based on data.
And my guess was correct. I knew you'd say that. So over my shoulder here is a QR code that will link everybody to this some research of yours. And we're at the hour, so we've kind of run out of time, but I'd like to express my deep gratitude to you coming on today to talk to us about your work on LNG. Keep up the good fight. We do cite your work on a regular basis in our own work on methane. And we've used a lot of your papers and a lot of your research when we are trying to understand how to approach these issues, what the arguments are. But to me, it's perfectly clear that LNG investments are an enormous risk, and they are very much at the whim of whatever political wind happens to be blowing. Because, as you said, for exports in the US, for example, they were banned, they were permitted, they're being pushed. Now they're being tied to tariff allowances from Trump. But in a few years, it's all going to change again. But in a few years, those pieces of infrastructure and those billions that were sunk into that infrastructure will still be there.
Exactly.
So these short-term political wins will are not reflective of the true long-term risks and costs of LNG investments. And I think your research showing that the true environmental footprint of LNG is critical. So thank you very much.
Thank you. Thank you. I appreciate the chance to talk to your audience and you today. Take
And
care.
we'll be sharing the slides for anybody who wants them, if that's okay.
Sounds great.
Fantastic. Thank you so much.
Thank you. Take care.